Okay, let's take a look at related rates of change. So this is another topic in calculus, and our labeling is going to be very important in this topic. And a lot of this is based on the chain rule, right? So just some instances of the chain rule that we're going to use a lot. So for example, if we're looking at the rate of change of the area of something, we're looking at the rate of change of the area, and the area is based on the radius, and the radius is changing with time. So we're looking at the area, which is based on the radius, and the radius size is based on time. So the radius is changing over time, and then as the radius changes, of course, the area changes. So if I want to get the rate of change of the area, dA dt, that is going to be dA dr multiplied by dr dt. Now this is technically the chain rule. We differentiate the outer function and then differentiate the inner function. All right. Similarly, if I have looking at the volume of something, and the volume function once again is based on the radius, which is based on time. If I want to get the rate of change of the volume, dV dt, that will be dV dr times dr dt. All right, so we're going to see a lot of this stuff today, and it's just important to understand that when you see it today, it's all coming from the chain rule. So to differentiate the volume, since the volume depends on the radius, which depends on time, the derivative is dV dr times dr dt times the derivative of the inner function. The radius is the inner function. That is, as I said, the chain rule. Okay, the other thing that's very important here is that when you see the word rate, rate is always a dt. Right, rate is generally got to do with time, centimeters per second, so it's a dt. So for example, when you see the radius is changing at a rate, well, that would be dr dt. If you see the area is changing at a rate, well, that would be dA dt. If you see something like the volume is changing at a rate, well, that would be dV dt. All right, so when you see the word rate, it's dt, and then the other letters made up of what we're talking about. So volume, dV dt, area, dA dt, radius, dr dt. So these are all kind of just introductory pieces to the puzzle. So the best way to explain this would be by aid of an example. So let's have a read of this question 1 here. All right. The radius of a circle is increasing at a rate of 5 centimeters per second. Find the rate of change of the area when the radius is 6 centimeters. Okay, so the radius is changing at a rate. That's what we were told. So if we go back and read that first sentence, we were told the radius changing at a rate is going to be dr dt is equals to, so the radius is changing at a rate of 5 centimeters per second. So dr dt is going to equal 5. All right, what else are we told? Find the rate of change of the area. So I'm asked to find the rate of change of the area. I'm asked to find dA dt. All right, that's what I'm looking for. So I have the rate of change of the radius. I have dr dt is 5, and I'm looking for dA dt, the rate of change of the area. All right, so from my chain rule situation earlier, to get dA dt, that is going to equal dA dr multiplied by dr dt. So I want to get dA dt. In order to get dA dt, I need dA dr multiplied by dr dt. Now I have dr dt. dr dt is 5, but I don't have dA dr yet. And where we'll get that from is the formula for the shape. So we're talking about the area of a circle. So your formula for the area of a circle, area equals pi r squared. If I differentiate that formula, I'll get dA dr. So dA dr is equals to 2 pi r. So I know that my dA dr is 2 pi r, and I know that my dr dt is 5. So finishing this, therefore dA dt is going to equal dA dr, which is 2 pi r, times dr dt times 5. So that is 10 pi r. And then to finish it, there's always a when. There's always something to fill in for r. So if we look back at the question, it says, when the radius is 6 centimeters. So I use that now. So at the point where r is 6 centimeters, my final answer to this question, dA dt will equal 10 pi by 6, which is 60 pi. And it's area, so it's centimeters squared, and it's a rate, so it's per second. Let's have a look at another question. The next question I'll do with you guys is question 4 here. All right, let's have a read of that. The area of a square with side length x is increasing at a rate of 100 centimeters squared per second. Find the rate of increase of the side when the area is 25. Right, so we're told the area, the rate of the area. So the area is increasing at a rate of 100. So that's telling me that the ADT is 100. That's what it's telling me. And it's asking me to find the rate of increase of the side. So I'm being asked to find, and the side is x, so I'm being asked to find dx dt. Alright, so I've been given the ADT, I'm asked to find dx dt. So the ADT is equals to 100, and I want to find dx dt. Alright, that's what I'm looking for. Now this particular situation, the area of the square depends on the side length, of course. The bigger the side, the bigger the area. So the area is a function of side length. So therefore, using my chain rule to get the ADT is dA dx times dx dt. Now what you have to realize here, guys, is I'm looking for dx dt. I'm looking for this. Right? I have my dA dt and I have my dA dx. Well, I will have my dA dx. I'm looking for dx dt. So what about this dA dx? Well, like the previous example, where I used this formula for the area of a circle to get dA dr, in this example, I'm going to use the area of a square to get dA dx. So area of a square is equals to x squared. So dA dx is going to equal 2x. So filling into my chain rule version here, dA dt, so 100 equals dA dx 2x times dx dt. So therefore, to get dx dt, just divide by 2x, so 100 over 2x is my dx dt. Right, so dx dt is 100 divided by 2x. And once again, there will be something to fill in for x. There will be something to fill in for x. So if we go back and look at the question, it says when the area is 25, right? When the area is 25. So if we have a square and the area of that square is 25, that means the side length x must be 5, because 5 by 5 to give me the 25. So at the point where x is 5. My final answer, therefore, dx dt will equal 100 over 2 times 5. So that's 10. And then it's a side length, so it's centimeters, and it's a rate, so it's per second. So that is 2 examples of related rates of change. Remember, a lot of it is based on the chain rule. All right, so you need to be familiar with the chain rule. And the other thing, we have to be very familiar with our labeling. All right, when we differentiate a equals pi r squared, that differentiates to dA dr. All right, so the labels on the left-hand side are very important. It's not just about what's on the right-hand side of the equals to sign. It's also about the labels on the left-hand side. We have to get those correct to make sure everything aligns the way we need it. So what you guys should do now is just practice some of these questions. Keep an eye on your solutions. And for access to questions, solutions, graded quizzes, and more, visit www.limbymaths.com.